So if we're going to look at oxidation, so one thing, it does say not. Make sure that you see that. So if we're looking at what chromic acid does, our chromic acid is what kind of an oxidizing agent? Good, strong, bad, weak? Yeah, this one's super strong. So when it oxidizes, it's going to fully oxidize. So when we talk about fully oxidize, okay, we've got a couple conditions that we need. We need an oxidizable hydrogen. Oxidizable. And then I'm just going to go out and just say an OH. Okay, and we'll come back to that OH in a second. So when we're talking about our oxidizable hydrogens and an OH, so let's ignore A for the moment because A doesn't have an OH. So let's go in and look at B. We for sure have that OH. When we're talking about the oxidation, we're referring to the carbon where that oxygen is connected. So we look at that carbon and I say, does that carbon satisfy the two conditions that I need? Okay. Do I have an oxidizable, or do I have the OH? Yes. Do I have an oxidizable hydrogen? The oxidizable hydrogen is a hydrogen that is connected to that carbon. Right? Again, not explicitly shown, but again, according to OChem 1, we should be remembering that to satisfy the octet, there's two hydrogens there. Does that make sense? So if we go through and look at that, that structure satisfies the conditions that we would need. Okay, so it should absolutely be oxidized. Okay, we're going to push on this a little bit. Yeah, we're going to do that. So if it goes through and oxidizes, it's going to start by removing the OH and our hydrogen. Removing the OH is a bit of a stretch. Okay, and set us up with the carbonyl. Okay, so we've increased the bonds to oxygen. Kind of, sort of? Okay. If we look to C, okay, again, we have an OH. We've got our carbon. Does that carbon have an oxidizable hydrogen? Yeah, there's an implied hydrogen there. So in the case of C, we would also continue this reaction. And we get our carbonyl. We go through and look at D. Does D have an oxidizable hydrogen? Okay, hopefully we're starting to recognize the value of finding our implied hydrogens. We do indeed still have an oxidizable hydrogen, so that should go through and oxidize. So we're going to turn that into an increased bond to oxygen, and then we'll still have that OH there. What happens in the case of E? Still have the OH. Oops, I meant to go color coding orange. But I don't have an oxidizable hydrogen. So at that purple position, which is not super obvious in the screen, okay, we already have a full octet there, so there's no implied hydrogens, which means that can't oxidize any further. Okay, and what does that tell us right away? That's the answer. Okay. Looking at I haven't scrolled down to look at the answer choices. Maybe it's a multiple select, but at very least we know this is a valid answer. Okay. I didn't look at A. Okay, so what's going on in the case of A? Does it have an OH? No. And if it doesn't have an OH, can it oxidize? Okay, and this largely has to do with the mechanism of how chromic acid works. The alcohol, the OH, is what's interacting with the chromium in our chromic acid. So if we don't have an OH, we can't continue to oxidize. Okay, and that's a really important statement in the overarching system for our oxidizing agents, our chromic acid and officially our PCC. Okay, but there's an extra piece of information that the question was nice enough to give us, and it's talked about when I talk about these reagents. is that remember that typical chromic acid includes water. So water is also present in this system. What could water do? Protonating the oxygen isn't going to be all that great right out of the gate. Okay, why not?
Because it's, water. Is it really going to donate on hydrogen?
Yeah, there it is. Water's not a strong enough acid. Okay, if you do want to protonate the oxygen, I'm cool with that because it's chromic acid. So you could go through and say that there is plenty of acid floating around with that. Okay, and you're right, that is going to happen, and arguably it happens first, but that didn't get to my initial question, which is what is the water going to do? The water is actually going to act as a nucleophile. Okay, so as a nucleophile, it can attack that carbon. That busts open that pi bond. Okay. Officially, if we're looking at the curved arrows here, I've drawn too many curved arrows for this to be a proper mechanism because I'm running an acid-base step and a nucleophile addition simultaneously. We're not allowed to do that as a formal mechanism. But as just predicting what our general products are, that's fine. We've got our water connected with the positive charge. Because Andrew was kind enough to note that we could protonate that other oxygen, we'll go ahead and show that protonation happening right away. We would end up with this structure as an intermediate. This structure as an intermediate is very unstable because it has the positive oxygen, so what can happen? Something basic steals the hydrogen. And before people go, but it's an acidic environment, that doesn't mean there's not something basic. Any oxygen can act as a base, as long as it's not positively charged. But as long as we have those lone pairs, that can act as a base and remove that hydrogen. Okay, which means in the presence of water, what I'm actually looking at in solution is a small concentration of this molecule. Do I have an OH? Yes. Do I have an oxidizable hydrogen? Yes. Which means that particular reaction will oxidize. It will continue down to get me the carboxylic acid. Okay. So there's a string of chemical reactions associated with that. What we tried to do is evaluate kind of our larger position of what the chromic acid does without getting too nitpicky into the details of the mechanism. But then we double back and look at kind of special cases with our carbonyls and say, what can those carbonyls do? We pull at earlier content of this unit, okay, officially going through the formation of a hydrate. Right? Once we have that hydrate, we have the OH, so now we can do that oxidation and complete that cycle. Okay. One question that would immediately come up from my perspective is that how likely is that first step to happen? The water attacking the carbonyl.
Not likely.
Yeah, not likely at all. Okay, so if we adjust the arrow there at that first step, I guess we'll call it red because I don't have red on the screen yet. That's what we're looking at. Our reaction says, I'm going to stay the aldehyde. Okay? And if that equilibrium is shifted that way, would I ever oxidize? And that is a very challenging question for the record. That's not an easy one. If that first step happens in such a tiny amount, would I ever actually oxidize? Would I ever end with the carboxylic acid? What do we think? Any ideas?
Wouldn't we want the acid to attack? I mean, would this hinge on the acid donating its hydrogen first, then making that carbon super positive?
That increases the odds of it happening, So if we protonate first, sure, there's my modification. It's still heavily favoring the carbonyl. Should I ever get the full oxidation of my product?
Is that for higher energy?
Technically, it's actually lower in energy. I would argue that's a conversation for the next unit, so we can kind of dodge that. And there becomes an interesting statement. Slowly it would happen. That very first step is not likely to occur, but an equilibrium will form. That equilibrium is going to produce a small amount of the hydrate. What does the hydrate do? Immediately reacts irreversibly to make the carboxylic acid. But I had an early equilibrium and I just removed that product. So what happens? It starts to form more of the hydrate that quickly gets funneled out. The equilibrium. I got to keep making that hydrate to maintain that equilibrium. So even though that first step is not a likely step to happen or happening at any real appreciable speed, it's happening enough that the chromic acid can then constantly siphon that product out, eventually converting all of the aldehyde into the carboxylic acid. Right? So if we're going to add chromic acid to the aldehyde, we will absolutely get the carboxylic acid, even though the linchpin of that step is the formation of the hydrate that we don't predict to happen at an appreciable amount. Does that kind of make sense? Right? That's drilling into the chemistry of that system. Right? You don't have to do that, but that's digging into the chemistry of how this works, and that's ultimately what differentiates chromic acid from PCC.
Would it have mattered on the fourth structure which OH you use?
Oh, so there's a good question. Fourth structure, so we're talking about this one here. Does it matter which OH I use? No. Okay, why not? Why does it not matter whether I use, we'll call it the black or the orange OH?
They're equal?
They're chemically identical. Since they're chemically identical, you're just going to get, if we could label them, you're just going to get a 50-50 mixture. Okay? So I just drew out a whole bunch of chemistry. We didn't have to do that whole bunch of chemistry. So we could have simplified this a little bit, and we could have just said that when I see that aldehyde, what happens?
It's turned into a carboxylic acid.
Well, and I started to look at the wrong structure. It gets turned into a carboxylic acid. Okay? So what we might want to do is change our summary out at this other end. But before we even get into that summary, what happened with structure 2? Did structure 2 form an aldehyde? Yeah, which means do I get the aldehyde? No. It's going to continue to oxidize because that's what chromic acid does. Okay? So again, question didn't ask it, but what we're starting to do is zero in on other ways that we could look at this. If we're going to look at the products of these reactions, this first one's going to be that, the second one's going to be that. How about the third one? Should that also go through to make a carboxylic acid?
That's the end.
Why is that now the end?
There's no hydrogens to.
Yeah.
It's that oxidizable hydrogen.
Get fewer hydrogens as you get more resistance.
Okay? With the fourth structure, we already evaluated that, fully oxidized. Okay? And then with the last one, we're missing that oxidizable hydrogen so it doesn't continue. So if we're going to try and memorize some information for our chromic acid, oxidizable hydrogen is useful. Seeing an OH is useful. But then we also want to address something about the extent of this. Okay? So the OH is going to show up in any of our alcohols. Okay, so that one's kind of straightforward. That was easy enough. But what we might also do is that we can say aldehydes. So we could memorize chromic acid is going to oxidize if I have oxidizable hydrogens, if I see an alcohol, or if I have aldehydes. So it's the OH or aldehydes. Kind of makes sense? And then we could jump to those answers. Again, in this case, it asked for the not. The only one that's that not is the tertiary, and that is because it doesn't have those oxidizable hydrogens. Does that help, Megan?
Yeah,
Other questions on that one, or we can move on? Okay. Okay, so what do we see? Okay, where do you see the reduction? Yeah.
Was it H2 reduction?
Okay. So, and actually, just pull these out. We have step 1, we have step 2, we have step 3. So step 3 is a reduction. What is it going to mean to do a reduction? Okay. So we could talk about the formation of an alcohol. That is one example of a reduction, though, because I could take this, the alkene, and turn it to the alkane. That's also a reduction, and there's no alcohol.
Adding the less electronegative.
So we can talk about the removal of a more electronegative element or the addition of hydrogen. Say again?
Electrons.
Yes, which is interesting because I would generally say, oh yeah, the electrons are obvious because it's OChem, but the electrons actually aren't super obvious, I would argue, in a reduction or the redox reactions within OChem. So if we're looking at a reduction, we can say the addition of H2, and that's kind of where you're getting your electrons because it's H2, one hydrogen's coming in positive, there's no electrons, the other hydrogen's coming in negative. So when you're talking about the electrons, those are the electrons that you're talking about that are coming in for that reduction. Okay, so in that analysis, what you did is you looked at the reagent and said the reagent does this. Okay? Is there any other evidence that you did a reduction? What about the product? So I would argue it's not the product by itself.
Some of our answer choices have.
But 3 out of those 4 answer choices are wrong. So I don't like that analysis. It doesn't necessarily have to be wrong, but
Plus, whatever that structure is called.
cool. All right. If we look to what given information we have, we've got our product and we have one of the chemical reagents. That chemical reagent, for the record, is known as formaldehyde. Don't stress about that. Okay? But that has a pi bond. If we go through and look at their product, we've lost that pi bond, so we could say addition. Okay? And we can also say that it was a reduction because I've lost a bond to oxygen. Right? So just those pieces would help you push through with the reduction. You can compare front to back, and you can also compare by just knowing the reagents. What does NaOH do?
Strong base.
Okay, so if we're looking at our reagents, we're talking about a base, which means potentially that first reaction is acid-base, followed by H3O plus, which typically acts as an acid, so at first blush, so we might be looking at another acid-base reaction, followed by a reduction. Does it make sense for it to be straight up acid base, and then our reduction? No, why not?
They just reverse each other. That's it.
So, perfectly valid argument. Didn't see that. Okay. If we did an acid-base reaction followed by another acid-base reaction, all we've done is undone that process. So it doesn't make sense. One of these should be something other than an acid-base. What's the other reason? If we do acid-base, all we're doing is adding and removing hydrogens. Right? The reduction, we're just adding hydrogens to the structure. If I look at the given piece of information, let's just say this structure, if I ran an acid-base reaction on this, I remove a hydrogen, I add a hydrogen, and then I reduce it. Why would that be a problem with this as a product? What's the part that I'm missing? All the carbons. I have to do some kind of carbon extension structure or extension reaction between those. Does that make sense? Okay. So there has to be some kind of carbon addition within that system. So one of these has to somehow bring in our carbon. Should the carbon come in as a nucleophile or an electrophile? Why should it be a nucleophile?
So it back our because it's the best nucleophile out of the.
Look at our given information. Why does this carbon thing have to be a nucleophile?
To add it on.
Okay, so if we're going to talk about a carbon structure, we're probably looking at this carbon being connected out to that oxygen. That linkage makes sense. What charge is that carbon in our starting material? That's positive, which means whatever this question mark is should be our carbon nucleophile, or at least have the capability of becoming a carbon nucleophile. Okay? In particular, it needs to be a carbon nucleophile that contains the remaining of those pieces, right? So, what could we start with? It needs to be a 6-membered ring. And I can draw it better than that. Okay? Which doesn't give us a whole lot because all of our answer choices gave us a 6-membered ring. Right? But if we now look at some of those pieces, right, we talk about that acid-base reaction wasn't good. I need a carbon nucleophile, right? What charge should the carbon be to be a carbon nucleophile? Negative. Which of those two reactions is going to be best choice to get me a carbon nucleophile? Adding a base or adding an acid? Adding a base. Why? Enolates, it's going to take a hydrogen off our structure, leaving behind a negative carbon. If we did it as an acid, all we're going to generate are positives within our solution. Carbon nucleophile needs to be negative. Okay, which might tip us off that this first step might be our actual addition with a carbon nucleophile, or intended to do that. So if we go through and look at this, which of those structures has the potential to make a carbon nucleophile by adding a base?
C and D.
C and D. Why only C and D? There's two explanations. I would argue. You could look at C and D and say the truth of why C and D are good. You can also look at A and B and say why A and B are bad.
A has no acidic hydrogens.
A, right out of the gate, there are no acidic hydrogens, so A should be gone. So adding a base to that does absolutely nothing.
B would create a negative oxygen.
Cool. B has an acidic hydrogen, but that acidic hydrogen's on the oxygen. That gets me a negative oxygen. I don't want a negative oxygen. I want a negative carbon. So we can look at our answer choices to say A and B must be out. Okay, why should C and D be in? Andrew gave us the negatives. Where are the positives? Officially, Andrew also gave us the positives, and I don't know why he chose to give us the negatives after he'd already said the positives, but I don't think he acknowledged that he did that.
That red
Resident stabilization of what hydrogen? The alpha hydrogens to the carbonyl, okay? Because you're forming the enolates. Why would I color the hydrogens differently on D? Yeah, that pi bond. Okay, that pi bond's going to change up the chemistry there a little bit, and so we might want to be careful with that. How careful do you think we should be with that? If I add a base to C, what's my enolate look like? Either hydrogen, I get the exact same enolate, the exact same carbon nucleophile. What does that mean for my products? I get one product. What happens if I do that to D? Oh, I could potentially get two products. So right out of the gate, I'm probably going to be like, I kind of want to lean on looking at C a little bit more. Okay? So let's lean into C. This one's got a lot of questions, or a lot of issues, I think, within it. Also a question I didn't write. Where are we? So our base goes through, removes the hydrogen, gives us our nucleophile. That's the end of step one. Now what? Actually, no, I was wrong. It does work. Say again. If the acid comes in, what happens? It protonates and it doesn't do anything useful. So I like what you're doing. You're thinking about your reagents, but you're only thinking about the stack of reagents. Isn't there another one? There's no grabbing oxygen. What's the other reagent? Your formaldehyde. So what can happen? This comes in, attacks, busts that. Green, we'd have our O negative. I don't want O negative, right? How can I fix that O negative?
An acid.
There's the addition of the acid. So now I'm going to delete that because I don't want to draw an extra step. There's my acid. Now what can I do? Okay. Now what I would need to do is get rid of that carbonyl. Okay. Reduction reagents, definitely a weakness of mine. I don't think Rainy Nickel does this. Okay. I think for this to work, it isn't just H2 and Rainy Nickel. Because I think if you do H2 and Rainy Nickel, I think what you get is this. And that's not the final product. So what was missing? You should actually run the dithiol reaction first. The dithiol makes this huge-ass, goofy-looking acetal-ish structure that now when I add Rainy Nickel goes through and replaces that whole thing with my hydrogens. And that gets me my final product. Say again? It's not a protection, it's actually activating it so that it actually does that reduction. So it looks like it would be a protection, but it's the dithiol is particularly reactive, or particularly susceptible to reduction. Where did dithiol bonds show up? Curly hair. So if you've ever had curly hair or wanted curly hair, it's usually due to dithiols, that your hair has a natural high composition of those thiol atoms within the hair fibers themselves, and that's what causes the curl. So if you wanted to get rid of that curl, You have to add chemicals and a straightener to it, and the whole point of the straightener is to do what? Break all those dithiol bonds, then you straighten the hair so that they can't see each other and curl up on themselves, because it's one part of the strand seeing another part, which causes the loop. So you add the chemicals to break those interactions and then straighten it so that they're away from each other physically. What eventually happens after you've straightened your hair? So I've been told. It eventually gets curly again. Okay? It takes time. What's happening in that time?
Cooling back down.
It is cooling, but if it was just cooling, how long would your hair stay straight? A couple minutes. So what's happening during that time that allows your hair to all of a sudden get back to curly? It doesn't work so well with my hair.
You're moving around.
It moves around, and so you're literally bringing those structures close enough to each other that they can chemically react and cause the curl again. And once it started to curl, it then proceeds to curl quicker and quicker and quicker because you've brought them closer and closer to each other until you have to chemically break all those linkages again. See? Who knew I was a hairstylist? I'm not. Make any sense? We good with that? Questions? Is that okay?
Yeah, that's good.
There are 3 reagents that add H and OH to a nonpolar pi bond. Or 3 reagent systems, I guess. What are they?
H3THF, H2O2, and NaOH for that, for either one.
Picked probably the hardest of all 3 of them to remember, but good job. I'm impressed.
That's the only one I remember, so.
What was that? Mercury. Okay, can you give me a little bit more than just mercury? Okay. Can you give me any more?
Acid, just H3O plus, something else? Or,
Yeah, I would argue the easiest of all of them, just adding H3O plus. Okay, so the mercury acetate, I will help you out just a little bit. It's 2 steps. What's the second step? It's not water, sorry. Sodium borohydride. Okay. These 3 reagents, I can't stress enough, I think you need to have memorized. You need to know the ins and outs for all 3 of these. So why would you choose one versus another versus another? Okay. So, what information do I want to add in this? I would call this a standard edition. All right, and by standard, what I'm saying is that it follows chemistry. All reactions follow chemistry, but it follows what you would envision of your normal chemistry. The mercury one, same pattern actually. It does our standard addition. Okay, so what are we talking about within that? If I drew a nonpolar pi bond and I drew something like this, right, and I want to add H and OH across the pi bond, what should immediately be a complication of this reaction? Because I add H and OH and I lose the pi bond, which means the H and the OH have to go to one of those two spots, right? Okay. So there's a couple different phrases that you could run with this, but generally speaking, this structure becomes a little bit more complicated than most because it's an asymmetric nonpolar pi bond. Okay? Because it's asymmetric, when I put the H and the OH on, I have to be real careful of the regiochemistry. Where does the H go? Where does the OH go? Okay? So what I'm saying standard chemistry, if I looked at this structure and considered its resonance contributors, I would say put the positive there and the negative there. Why? Positive is more stable when it's more substituted. Negative is more stable when it's less substituted. That's the valid location of where those charges are. Where's the standard chemistry come into play? That's part of it. The other part of it is I'm adding H and OH. What's the standard chemistry of H? So I'm going to put the H, I'll put the H there. And what's the standard chemistry of an OH? Negative. So I'm going to put the OH there. That's standard chemistry in my mind. Okay? If we go and look at how I've summarized this at the top, it says H and OH. It does not say H plus and OH minus. Okay? Because we have to be real careful with the charges associated with those. Okay, why? Take a look at the very first one, BH3, THF, and NaOH. Where's the OH? I'll accept a couple different answers for this officially. Where's the OH? In the very first reaction, the BH3 one. BH3 followed by H2O2 and OH minus.
In the second step.
It's in the second step. Where in the second step is it?
The NaOH.
I will fully accept that. It's wrong, but I will fully accept that. Okay? It's officially coming from the H2O2. Okay? The NaOH is a lot easier to deal with, so we're just calling the NaOH. What is the charge on the OH in NaOH? It's negative. So our oxygen is coming in as negative. Where's the H coming from? Say again? BH3. Awesome. What is the charge on the H? It's negative. BH3 supplies a negative hydrogen. Difference in electronegativity, how the boron reacts, all of that contributes to that. Okay, so that's going to change and move into now what I would call non-standard chemistry. Okay, again, it's not non-standard chemistry. What happens? Well, the first step happens first. Where does the H minus go?
More substitute.
It goes to the more substituted spot. It's going to go to the positive. Okay. Where does that mean the oxygen has to go? It's going to have to go to the least substituted. It's following up. It's in secondary chemistry spot. It can't now all of a sudden roll off the hydrogen and swap its place in. The how that happens is the mechanism behind how the boron reacts and all of that fun jazz. That can be challenging. Okay? The cheat that people go through and use, instead of calling this standard addition and not standard addition, they would call this, whoops, I can't even spell a name right. Markov. Shit. Fuck. Period. And anti-Mark. Okay. A colleague pointed out that anti-Markovnikov becomes challenging because we use anti in other circumstances. So it makes sense to actually not memorize it as anti. You can memorize it as not Markovnikov. Okay. That's fine. I'm okay with all that context and nailing this down. Okay. Does that kind of make sense? Okay, so those are the big things that are really need you to remember behind that. There's a bunch of extra secondary pieces that go with this, okay? But all of that was kind of a distraction for why we're bringing this up. I want to double back and look at this mercury reagent just a little bit more carefully. Okay, so we're going to ignore almost everything within this. Shouldn't have erased all that. And I just want to look at this step, but I just want to look at it in the case of our mercury reagent. Where does the H come from? BH4. Completely agree. Okay, and I think I even heard someone say minus. Like, oh, well, if it's minus, shouldn't it be doing the opposite? But remember, okay, that's in step 2. I care about step 1. And what's going to happen in step 1?
It's going to react with the positive.
So we can talk about the mercury going through and reacting. What else needs to happen in step 1? Remember, 2 things happen to get to your product. You've added H and OH. Step 2 brings in the H. What must step 1 bring in? The OH. Do you see OH?
No.
Ooh. There's the problem with what you've got memorized. Okay? When we talk about that reaction, there's an extra piece here. We have to have that OH. Okay? That has to somehow be supplied in this particular scenario. How could I supply that OH? Okay? And now we're going to encounter an interesting dilemma because the suggestion we got, methanol, ethanol, we're going to do methanol because it's shorter. Okay? So we're going to take a step deep dive and look at our mechanism. Andrew, what was your mechanism description? Because it was pretty good. You started it, and then I wanted you to do something else.
Is it this?
You got to draw it?
I gotta draw it out. Yeah.
That's fine.
Was that HG acting as the nucleophile for the positive carbon that we're forming in our...
Okay, and we encounter a whole bunch of different things because it does a lot. Okay, the HG acts as an electrophile for our carbon, but it also has that lone pair, which I conveniently drew on the opposite side of where I wanted it to, and that can come back down.
Oh, so it's the three.
Yes, this is the 3-membered ring. Okay, what context do we have to know it as the 3-membered ring? Well, if we finish our structured out OAC, OAC is what? I know. Horribly vague questions. Okay, so we saw someone naming that structure that I drew in green is acetate. So OAC is the oxygen connected to an acetyl group. That is acetate. What else or how else could I describe that structure? And not just a leaving group, it's a good leaving group. And if we go back and look at the lectures when we talk about these non-polar addition reactions, if we have a good leaving group, we end up with a 3-membered transition state or a 3-membered intermediate. Here we're going to pull an actual 3-membered intermediate, and we've got our mercury connected in there. Loss of the pi bond, there's our structure. Okay? This sets us up with a bit of a problem. What's that problem? If we pretend for a moment that we forgot about the source of the OH, our next step would be BH4. And what happens? You add hydrogens. Where did the oxygen come from? It can't come from the acetate because the acetate's a good leaving group. That's effectively unreactive. Okay, so if we have some of that mechanistic information, that can help guide us that we missed a piece. So let's decide what that piece was. So the suggestion was HOCH3. What does that reagent do? could,
Okay.
but I'm not drawing anything because it doesn't. The lone pairs on that oxygen come in and they attack the more substituted spot. Why? Mercury is charged, really doesn't want to be charged, and so it's already trying to leave. So our oxygen comes in and attacks. Why does this become super important? Well, now we would continue through. We've got our bond out, we've got our bond up to our mercury. We would have our oxygen there, right? An oxygen connected to what? A methyl, yes, and an H. It's also charged. It's positively charged. How do we fix that charge? A base. The base does what? Removes the hydrogen. Did we add OH? No. Okay. So one of the things that gets a bit dodgy with how, even I've written it out, I said, we add H and OH. I would argue we're not adding H and OH, because when we talk about additions, sorry, Andrew. Okay. An addition is the formation of two new sigma bonds and the loss of the pi bond. When we're talking about this addition, it's the addition of H and it's the addition of O. That O has to be satisfied with something else. That can be anything, any kind of R group. And if we make it a CH3, that's what happens. I have to have an H out here to be chemically reactive. Why? Because I needed to remove that H after the nucleophile attack. Okay? Whatever that R group is going to be the remainder of my piece. So if I wanted to add HOH, I don't add methanol, I add water. One of those hydrogens gets removed in a later stage. Okay, so we've done the addition of our oxygen. The BH4 comes in, effectively cleaves the mercury and replaces the mercury with a hydrogen. Okay, why does this become really important? Every time students go through to memorize this, they go through and memorize the mercury adds H and OH. I'm guilty of this too. No, it doesn't. It adds H and O. Okay, that extra piece, whatever decides to stick with the oxygen, is effectively our R group, and that can be pretty much anything. All right, questions about what's up here? Because we've got to delete it to get to the point for why I went through and did this. Okay, it is now deleted. There, so much for the dramatic pause. What the hell? ACS will frequently ask this question. What do you see right away at the bottom of this? Hopefully we see nonpolar pi bond, right? And mercury. Oh, what does mercury do?
That's OH.
It adds H and OH, which means all I've got to do is now quickly scroll to my answer choices and be like, which of my answer choices added H and OH? Well, 1 did. 3 and 4 did. But 3 and 4, I'm smarter than that. I'm not going to fall into that trap because I know it adds it in a normal fashion. That normal fashion looks like answer choice 1. The answer must clearly be 1, and I move on. Why does it add OH? Because the R group was H. The R group in this case is not H. What does it actually add?
Methyl.
Saying it adds a methyl is a little bit of an overstatement, but I get where you're going. It adds the H and OCH3, the O methyl. Okay? So watch out for that subtle change in the reagent. And if you look at answer choices, you try even just test-taking strategy on this. Test-taking strategy says which answer is wrong.
2.
Test-taking strategy says 2 is wrong. Because we got 3 answer choices that show OH. They're literally putting it on the exam because they know students aren't paying attention to where the oxygen is coming from. You're ignoring the reagent. So make sure you pay attention to the reagent as you navigate this. Does that make sense? Why else does 1 not make sense? This was actually me trying to be nice. Say again? It shows stereochemistry. Why is that wrong? There isn't a stereocenter in 1. Showing stereochemistry is 100% irrelevant. Okay? So you could, oh, well, I have to show the other one. Show the other one. It's the exact same structure. Right? So I intentionally drew the stereochemistry in there to hopefully set off a few alarm bells to be like, wait a second, this doesn't look right. Right? Sometimes it works, sometimes it doesn't. Believe it or not, I do look at that refined thing of how can I get just a little bit more information in there that might help somebody fall into the correct alignment. Kind of make sense? So that when you go through and look at the answer choices or the things that were selected by your classmates, okay, the first one said D, a mixture of 3 and 4, okay? You are adding the H and the OH. I like the kind of thought process, and you're recognizing that those are stereocenters, and therefore you would need that, but unfortunately you didn't add OH. Okay? And unfortunately, it doesn't add in that way. The mercury reagent does the normal addition. Okay? And then the next answer got it right, but the description was really wonky for me, so I couldn't quite figure out what's, oh, that's what the description was. Got the answer right, B, yes, it's just 2, but then starts off with saying OH is added at the most substitutes. It's not OH, it's OCH3. Okay? Kind of makes sense? So when we talk through the practice exam, it's this kind of stuff that I'm trying to find within it. This is why I don't want to post answers, because if I post blanket answers, we don't get this, and that happens when you take the test. So here we can look for those, whoops, you made a real subtle mistake. I can highlight that subtle mistake, not to be a jerk, but to make sure it never happens again. Make sense? And added benefit, everybody gets to see everybody's mistakes. Right? Again, not to be a bad thing, but to point out we will all make mistakes. That needs to be brought forward so you can acknowledge that you're not failing. You just have to work through and fix those mistakes. It's okay. And just because I saw a cursor pop up, please don't ever edit your answer once it's there. Okay? Because if we go through and look at this, if whoever said B changes this now to OCH3, does my response make any flipping sense? No, it's not going to make any sense. Okay, so if you're seeing a comment from me of like, I don't like this, you need to fix this, fix it below my comment so we can see the thread of thought. And sometimes, because I see Tyler's face already, it makes me, sometimes my comment doesn't make sense to you. That's okay too. Reach out and be like, Mike, this doesn't make any sense. But, oh no, I thought that was hilarious. Right? Review that response, then look at this response, then look at that. It's an Old Spice commercial, come on. You're almost too young. Okay, in any case, should have paused that like 30 seconds ago. Talk about a potential risk of elimination. That is technically okay. Why is C a wrong answer? count your number of carbons. C is entirely wrong because if it had produced your product, it's not going to produce the product that's actually being shown. You would be putting 2 carbons into your chain, not the T-butyl or the methyl. So there's actually 1 too many carbons. Does that make sense?
What even is this question asking?
Okay, so we can double back a little bit differently.
It just look like
Okay.
words.
Well, it is kind of a word question. So, which of the following is an acceptable starting bromide in the ether synthesis of MTBE? So you might be like, I don't know any of these words. Okay, well, you should know some of these words. Okay, it says synthesis of structure shown, which means reaction arrow, right?
Okay.
And then it says starting bromide. So I need to have a carbon structure connected to a bromide. And if I had a carbon structure connected to a bromide, what else would have to react with this to get this piece? I would need some kind of negative oxygen connected to some other carbon structure. So if we're going to go through and try and evaluate this, what we would need to go through and do is say, well, how did I make that bond? Was this O carbon like that? Okay, if that was the case, we're saying we have OCH3. Did I really just draw the answer? Stupid. I'm looking at that as my starting structures. Or is it OC that direction? With this, whoops, as my starting structure. Does that make sense?
Yeah.
Okay. This format of a question does show up. It doesn't show up a whole lot. Okay, so more often than not, you're going to be looking at what's the product, what are the reagents. Okay, you typically don't get it written out as a all in words, and then you're expected to come up with that interpretation. But it does show up, so I need you to have some experience with it.
Okay. So it's not both.
Why can't it be both? I actually didn't draw the answer right away. What can these negatives act as?
A base.
They could act as a base or a nucleophile. We want them to act as a nucleophile. Could they act as a base?
Yes.
Okay. If I acted as a base and removed that hydrogen for this bottom one, how would I stabilize that structure?
It wouldn't be stabilized at all.
It wouldn't be stabilized at all, which means can it act as a base?
No.
No. How about in the top case? I'd form that same deal, negative carbon. Could that act as a base? Could I stabilize that? I can get the elimination reaction happening in that case. Does that make sense? Okay. So when you're looking at this type of a question, yes, there's a branch point, and the question is going to become what becomes the best option. These are very challenging questions because on the surface, both answers do exactly what you want them to do. You also have to check all the things that you didn't want it to do. Right? So anytime you see a nucleophile, it can act as a base. Is that possible? If it is possible, that's going to decrease my yield. So tons of arrows. Where should you start? Okay, we could start with the starting structure. What chemistry do you have for the starting structure?
Oxidization. Or I mean, the mechanism is that.
So when we say we're starting with the starting structure,
In an OH there.
so what chemistry do I have? I have an acidic hydrogen. I have a nucleophilic or basic oxygen. I have an electrophilic carbon.
I think that.
Okay? You see where I'm going with that? So the starting structure isn't a bad place to look. So I fully acknowledge I want you to be able to do that. But to making progress through this question, you need a whole lot more context to help navigate this. Okay? And that's where, yes, looking at your reagents can come into play. Okay? And that's now going to come down to, well, what comfort? Where are you with your reagents? Have you started looking at these? Are you familiar with what they do? Okay? So within these three, if I were to rank what I think you should be comfortable with, personally, I would say you should be comfortable with this one first, more or less, this one, and then this one last. But that's me guessing at what you've been doing. Why would I put that ranking up there? What's this reagent? That's Vidig. We did that a long time ago. You should be more comfortable with that. Okay? You sort of have talked about that one. Okay? So that should be more of a review. So to that statement, I would argue that's a pretty good place to potentially start because you know those reagents a little bit more. I would argue 2 is a real close second, and 2 should be a real close second because we've now talked about it this week multiple times. Okay? So that's why you should be familiar with what's going on with part 2. And I would argue that last one, it's a freaking red herring coming out of nowhere. I think we looked at maybe a question actually no, it was one on my schedule that I was going to talk through in class, and we didn't get to it. Okay? So where's your comfort? Your comfort needs to dictate how you would start and approach this. Okay. So in that discussion, Tyler said we should look at the starting material, which we looked at, and ultimately, hopefully kind of agree that unfortunately that's not particularly useful for us because there's just too much going on. But if we keep the starting material in mind and layer in potentially Andrew's statement that we know what PCC does, that would get us immediately to a structure that would allow us to then branch out. So even if I started with the Vidig stuff, I have no idea what I ended with. I have no idea what I started with. Okay, so there's not a whole lot of structural pieces I could put into that. Does that make sense? Okay, so what does PCC do? Okay, it's a weak oxidation. And by weak oxidation, what does it mean? The weak oxidation does a single oxidation. Converts the alcohol to the carbonyl. Okay? Could I have used chromic acid to do the same reaction? Yeah, chromic acid is a strong oxidizing agent. There weren't multiple oxidizable hydrogens, so either reagent would have been fine here. Okay? Would argue people like using PCC because it gives you zero context clues about what's actually happening within it. If we'd written out chromic acid, we at least have a structure that we could work with. Okay, so cool. Compound what? A is that carbonyl. So now where's your comfort level? What do we do next? Right? We got a suggestion for the Wittig. What does the Wittig do? The Wittig, we have our carbon, acts as a nucleophile, comes in, breaks that. We form kind of a gross structure. The phosphorus reacts with the oxygen to form an even grosser structure. Ultimately, the oxygen and the phosphorus get kicked out, and we form pi bond with our carbon. So the Wittig replaces the oxygen of our carbonyl with the central carbon. Right? We want to be a little bit careful. The hydrogens can be R groups. Okay, so those could be anything coming off of that. The chemistry is that circled carbon. What does the H2 and the nickel do? A reduction. Do I have a pi bond to reduce? Yeah, so what happens? I lose my pi bond. I could go through and show that hydrogen if I really wanted to. Right? Do I need to worry about stereochemistry? Yeah? Why? Where do I have a stereo center? Okay, we'll call it the blue carbon as a stereo center. What is this black carbon? Tell me what atoms are connected there. 3 hydrogens. So that would be a carbon and 3 hydrogens, also known as a methyl. What do we have up here? We don't actually have a stereo center.
Yeah.
We didn't need to worry about it. Okay. If we did have to worry about it, the 2 hydrogens that we added need to be added. How?
Different. Like,
Same.
yeah.
Not different.
I
Same
mean-
side.
I was getting there.
That's fine. Right. But here we didn't need to worry about stereochemistry. We could just draw that out. So that would be our compound B. What happens in the bottom one? Could do this a couple different ways. What is this reagent or sequence of reagents? The Wolff-Kitchener reagent. Is it a double F? No? Okay. I don't know. I feel like it looks not right. Okay, but it's the Wolff-Kitchener reagent. So if you memorize what that reagent does, you've got that. This is one you probably did see? Based off of me or the internet? What's that? Internet. Okay, good. This is probably not one that you want to derive, because mechanistically, this is a lot of steps. Okay, I think this one beginning to end approximates like 15 to 16 mechanistic steps. Okay, with over half of them, probably 10 of them, are acid-base reactions. Okay, so this is one that probably makes sense to just include in your memorization. What does it do? What's that? No? What's it do?
It's 2 hydrogens there, right?
Yeah, I accept that. Puts 2 hydrogens there. And by there, you mean like that.
Yeah.
Yeah. Do I need to show the hydrogens?
Nope.
No. So this is a full reduction. Okay. Why is the Wolff-Kitchener useful to memorize? So you don't have to do all the steps, and there's also the Clemenson reduction. What's the third one? It's not named, I think. Or is it named? There's 3 reductions that you need to be aware of. Oh, the rainy nickel. Okay. You've got 3 reagents that all do ultimately the exact same thing. Sounds kind of familiar. It kind of sounds like the H and the OH that we just talked through. Okay? You've got 3 reagents that do exactly the same thing that screams a multiple choice question. Okay? So you need to be able to differentiate those reagents from each other. Okay? And as much as I would love to discuss the details of those 3 reagents, I actually don't. We're done with lecture.